let's start. So today I'm very happy to have Professor Shagnik from National Taiwan University. And Shagnik worked on combinatorics, which is a missing research field in our department. So I hope our students to enjoy this talk. Let's welcome speaker.
Thank you very much. Good afternoon, everyone. It's a great pleasure to be here speaking to you today, and thank you to the organizers for giving me this excuse to leave what's a drizzly and rainy Taipei and to come here to Hsinchu. And the weather today is really putting the Qing and Qing. So I'm going to be talking to you about a problem that's kind of captured my attention for the past few years, something that I've been working on in a couple of different projects with various people. So it's about covering grids with multiplicity. It's a problem in combinatorial geometry or extremal combinatorics. And so the kind of new results I'll present to you today are joint work with, the main focus will be work with Anurag Bishnoi, Simona Boyajiska, and Yvonne Den Bakker. But I'll also mention some results I've done kind of locally after moving to Taipei with Valyakas Dialjapayan, Yanchi Roger Lin, and Wei Xuan Yu. Okay? But as was mentioned, this will also be more of an advertisement for combinatorics as well to get you interested in this subject. So the talk will split into two parts. In the first part, I'll talk about the classical problem of covering grids. Okay, so this is a problem that goes back to the 90s, which maybe isn't that long in mathematical terms, but for combinatorics, it does make it a well-established problem. And then in the second talk, I'll talk about the problem that we were actually working on, which is this multiplicity version, which is something that has been studied more in the last 5 years or so. Okay. So to warm up and give you a flavor of the kind of problems we will be talking about, this is a kind of first question in this direction. So here we have a grid of points in the plane, the real plane, you can think of it. And the question is, how many lines do I need if I want to cover all of the points of this grid? Okay, so I'm using straight lines, and the question is, how few lines do I need to cover every point on this grid? Okay. So now, if you're going to work on a question, or if you're going to sit in a talk for an hour about a question, then you should always know why you're doing this. Okay, so I'll give some motivation. Even though this is an attractive problem in its own right, there are some good reasons for studying it. Okay, and so some personal motivation, which attracted me, is that nowadays you young people have a lot of very interesting ways to spend your free time. Okay, but back when I was your age, we didn't have such fancy technology. Okay, so we had much simpler games, okay, which weren't quite so interesting. And one classic is this game called Pac-Man. I don't know, have any of you played this game or seen it before? Okay, so the goal is that you control this little guy here, and you want to go around eating the cookies. Okay, so this is what it looked like. But now if you wanted to play this on a very simple mode, you might have a grid like this. Okay, and then you want to go around the grid, trying to get all the cookies. And now you can imagine perhaps, these arcade machines, they weren't so reliable. Okay, and so maybe the joystick was broken and you weren't able to turn. So you could just move in straight lines, and then the question would be, how many lives would you need to eat all of the cookies? Okay, so how many lines does it take in order to cover all of these points? Okay, so that's the motivation for this problem. Okay, whether it's convincing motivation or not depends on how you like to spend your free time. But here we go again, just looking at it in purely mathematical terms. And now this, as I said, is just a warm-up question, so it's not too hard to answer. Probably many of you have answered it already. So if you have an m by n grid, where n is at least m, then it's not hard to see that you need at least m lines to cover everything. Okay, and m is possible, so I can just take the horizontal lines, I cover all of the points. And now the question is, why is this the best possible? Why can I not use fewer lines? And if I had less than m minus 1 lines, at least one of these horizontal lines has to be missing, right? And so if one of the lines is missing, then there are n points on that line, which I still need to cover. But the point is that any other line can cover at most one of these points at a time, right? Because any two lines can intersect in at most one point. So I would need n lines to cover these points. And so either my cover has the m horizontal lines, or it has at least n lines to cover all the points from this line. Okay, and so that shows you that m is the best possible. So that wasn't a very difficult problem, okay, and that's not the kind of problem which you would spend years studying. So the question is, what are we really interested in? And so we're going to change the problem slightly. Okay, so we're going to have the same grid again, and the question will still be about covering points, but now there's going to be one forbidden point, which we're not allowed to touch. Okay, so we want to cover all of the points in the grid except this one point, which we have to avoid. And again, you can ask, well, why would you do this? Why is there a forbidden point? So if you think about our motivation, there might be a ghost on that square. Okay, and if you touch that ghost, you lose the game. So you want to eat all the cookies and avoid the ghost. And now, if you think about the cover we had before, so before we said, okay, take all the horizontal lines, but now, of course, you're not allowed to do that anymore. Okay, because the bottom line is illegal. And so if you remove the bottom line, then you still have all of these points left to cover, but again, you can only cover them now one at a time. Okay, so this becomes quite inefficient, and instead of needing m lines, you now need m plus n minus 2. Right, n minus 2, because you got rid of one horizontal line, and you don't need one vertical line, so minus 2, but otherwise you gain a lot of points. Okay, so this is an answer. This gives you an upper bound to the problem. But the question is, well, can I do better? Maybe I can take a very different type of cover. And it turns out that there are different types of covers. If I use diagonal lines, I can cover all the points. I avoid the forbidden point. And one thing to notice, one key difference between these covers, is in this cover, almost everything gets covered 2 times. So it's quite wasteful, right? Because I only need to cover things once, whereas in this diagonal cover, I only cover everything exactly 1 time. However, I still need a lot of diagonal lines. And it turns out that you need exactly the same number, m plus n minus 2, with this very different cover. Okay, so both of these constructions, they're valid, but they give you much bigger answers than your previous one. So then the natural question is, can you do better? Okay, is there some cleverer cover which isn't so wasteful and uses fewer lines? And this problem turns out to be not so easy to solve. Okay, and in fact, it was a theorem, the theorem that kind of started this line of research, from 1993 of Alon and Furedi, who are some very famous combinatorialists, and they showed that no, you cannot do better. Okay, but when they wrote their paper, they didn't just write no in the theorem. So if you want a formal statement of the theorem, in this setting, it looks something like this. So I have 2 sets, 2 finite subsets, which are the coordinates of the grid. Right? So the x coordinates and the y coordinates, and now you have the grid, the Cartesian product of the sets, and you want to cover all of the points except for one forbidden point. And they showed that if you do this, then the number of lines you need is n plus m minus 2. Okay, so the same bound that we had before. And one important thing to notice is that this works over any field. Okay, so there were some results known previously over finite fields, for example. This, I believe, was the first result which works over the reals. And we need to think about what this means, okay, or why this was such a difficult problem. And in order to prove a lower bound, you need to show that any possible cover has to have very many lines. Again, if you think about it, there are many, many different ways you could try to cover the points. Right? If you have n times m points, you have n times m choose 2, or n squared m squared, many possible lines. Okay, and any combination of them, the theorem shows you need to have many different lines in order to cover all the points. Okay, so it's not so clear how you would even try to do that. Okay, and it turns out, as we were talking about over tea time, that algebra is the missing ingredient here. So even though the statement has nothing to do with algebra, right, it's a purely finite or discrete geometric statement. It's about points in a plane, okay, or a 2-dimensional vector space, if you like. So there's no algebra at all in the statement. Okay, it turns out that you can prove the lower bound using algebra. And in fact, kind of more significantly or more surprisingly, perhaps, the only proofs we know of this theorem are algebraic. Okay, so we don't know any way to prove this just using combinatorics or just using geometric arguments. So let's look at how the proof works. Well, the idea is that if I have any cover, if I have any set of lines, I'm going to associate a polynomial to that cover, which represents all the lines in the cover, and I'm going to show, or I'm going to set it up in such a way that the number of lines in the cover is going to be at least the degree of this polynomial. And then I'm going to show that any polynomial which corresponds to a cover has to have large degree. It has to have degree at least n plus m minus 2, and therefore I'm done. Okay? So let's see how we can do this correspondence. So notice that the problem doesn't change if I shift my grid in the plane. So I can assume that the forbidden point is the origin, 0, 0. Okay? And then if I look at any line which is in my cover, because I know the line doesn't go through the origin, I can write it in this form. ax plus by is equal to 1. Right? I can rescale the coefficients as needed. So I can write every line in this form. Okay? So every line corresponds to this linear term. And then what I can do is if I have a set of lines forming a cover, I can look at the polynomial, which is the product of these linear forms. Okay? And so I now have the product of these, and that gives me a polynomial. It gives me a polynomial in two variables, okay, x and y. And then the key thing to notice here is that the degree of the polynomial is exactly the number of lines in my cover, right? Because everything here is linear, so for every line I get 1 added to the degree, okay? And then the key property, right? How does this represent a cover? Well, the point is that if I have a point on my grid, which is not equal to 0, so if I have a point covered by a line, then on that line, this linear term will be 0. And since I'm taking the product, that means the whole polynomial will be 0. And on the other hand, since the polynomial is a product of these linear forms, it will only be 0 if that point is covered by a line. Okay, so if you're familiar with algebra, then we're looking at the variety determined by this polynomial. But what we're saying is that I can tell when a point is covered by a line in my cover by evaluating the polynomial at that point. If it's 0, that means it's covered. If it's not 0, that means it's not covered. Okay, so I have this correspondence. And so, yeah, again, putting that into our problem, that means at the origin, the polynomial is non-zero because none of the lines touch the origin, and every other point of the grid, the polynomial has to be 0. And so now I'm just going to look at polynomials with this property, and I'm going to show that they should have large degree. Okay, or that's the idea. But again, there are very many possible polynomials. Okay, so to make our lives a bit easier, we want to restrict to some nice types of polynomials. Okay, so we're going to look at a nice subspace of the polynomial ring. Okay, and in order to kind of reduce the type of polynomials we're going to look at, notice that if I look at this polynomial, where again I have some grid, right? The coordinates are determined by the set x, and I'm going to look at the product of x minus a for every possible coordinate, every possible x coordinate on my grid. Then if I have any point on the grid, this polynomial will always be 0, right? Because the x coordinate comes from this set x, so for one of the a's, that will be the x coordinate of my point. So this polynomial is 0 everywhere on my grid, and the degree of this polynomial, it's only a polynomial in x, the degree is exactly the size of x, the number of coordinates, or the dimension of the grid. And I can do the same thing for the y coordinates, right? So for the height of the grid, I get a polynomial of that degree, which is identically 0 on my grid, right? Because I only care about points on the grid. Points off the grid aren't important for me. Okay? So I have these two polynomials, and what that means is if in my polynomial, right, the polynomial is a product over all of these lines, so I could have some very high degrees of x, high degree terms in x, or high degree terms in y, but I can always reduce them using these polynomials. So if I have an x to the size of x term, I can replace it with x to the size of x minus this gx polynomial, and on the grid I don't change any of the values, because this gx term is always 0 on the grid. However, this gx is a monic polynomial of degree x, so this leading term is going to cancel out. And so I reduce the degree in x without changing the value on the grid. Okay, so I could change the polynomial elsewhere, but again, I only care about what happens on the grid, so this is a legal chain for me. And I can do the same thing again with the y terms. Okay, and so if I keep doing this reduction, then I can bound the degree of the polynomial. Okay, so that means after I keep doing the reduction, the largest power of x I see will be the size of x minus 1. The largest power of y I see will be the size of y minus 1. Okay, so now I have a very finite bound on my degrees. Okay, and after I do this reduction, I get a new polynomial, so I'll call that f tilde instead of f. And so, again, what are the properties? Well, as we said, on the grid, the values don't change. So f tilde is still non-zero at the origin, and it's still 0 every other point of the grid. Okay, because it's the same as f on the grid. And the degree of f tilde cannot be any bigger than the degree of f. Okay, and in fact, it could be reduced, right? Because I'm reducing the degrees of the x term and the y term. So the degree of the new polynomial f tilde is at most the number of lines in my cover. And most importantly,
this f tilde, it lives in a finite dimensional vector space because it's a polynomial, so it's a linear combination of monomials, but now these monomials have bounded degree. So the largest power of x will be the size of x minus 1, because if there is a larger power, I would have reduced it using the gx polynomial. And the largest power of y is the size of y minus 1. Okay? So I have a bounded number of monomials which span these polynomials here. Okay? And in fact, so this is one possible basis. I could take this monomial basis for the polynomial ring, but there's another basis we can take. Right? So let's think about how big this basis is. Well, the number of monomials here is the size of x times the size of y. Right? Because the degrees can be anything from 0 up to the size of x minus 1, and 0 up to the size of y minus 1. Okay? But the size of x times the size of y is also the number of points in my grid. Right? And I can come up with a different basis centered around the points in the grid, where I take the product. This looks like the g of x polynomial, except I exclude the x coordinate of that point. And this is like the g of y polynomial, except I exclude the y coordinate of that given point. So this polynomial will be 0 at every point in the grid except the point AB. Except the point UV. Okay? So at one point on the grid it's non-zero, everywhere else on the grid it's equal to 0. Which is very much like the polynomial we care about. Right? Because the polynomial we care about is 0 everywhere on the grid except the origin. And it's not hard to show that these polynomials, so they lie in the same subspace, right? Because you can expand the monomials, right? And the largest degree of x is the size of x minus 1, largest degree of y is the size of y minus 1. So they still lie in the same subspace, but it's not hard to show that they form a basis, that they're linearly independent because of this property that they're non-zero exactly at different points on the grid. Okay, so there's no way you can get any cancellation. And so now we can put all these ingredients together to prove the theorem. So suppose we have a cover of the grid which covers all the points except the origin. We formed a polynomial FL by taking a product of the linear equations for the lines. We reduced the polynomial to bounded degrees without changing its value anywhere on the grid. So we get this f tilde. Now we said f tilde is 0 if and only if, it's non-zero if and only if you're looking at the origin among the points on the grid. And so if we use that point basis that we just set up earlier, that means it has to be a linear scalar multiple of the basis polynomial centered at the origin. Okay? But now we know exactly what that polynomial looks like, so we know what the degree of this polynomial is. The degree of this polynomial is the size of x minus 1 plus the size of y minus 1. Right? So just to look at this polynomial again, so here I get the size of x minus 1 linear factors. Here I get the size of y minus 1 linear factors. Right? So the total degree of the polynomial is exactly the bound I'm looking for. And this is a lower bound of the degree of f, the original polynomial, which is equal to the number of lines in my cover. Okay? And so that's the proof. So are there any questions about the proof? So I know that this is probably a new topic for many of you, but hopefully the proof is something, it's a so-called elementary proof that you can understand without any special knowledge of combinatorics. And again, it's a very surprising proof because there's no reason why polynomials or algebra should come into this at all. Okay, and especially because this is the only way we know how to prove this theorem. And so kind of this, I'll talk about this in a bit, but this became an important theorem because it led to the introduction of this algebraic method in combinatorics. Okay, and it's often a powerful tool when you have many different extremal constructions. So we saw before that there's this construction with the horizontal and vertical lines, but there's also this construction with the diagonal lines. So if you have a proof that this is the best cover, your proof needs to work for both of these types of constructions, or any more. So doing it with induction or something is a bit difficult because these look very different from one another. But the reason why algebraic theorems can work, algebraic proofs can work, is because here we're using the fact that we have some basis of a vector space. And in a vector space, you can have many different bases of many different kinds. Okay, so it's a more flexible proof somehow that doesn't depend on the precise structure you're using. Okay, so now that was in the plane, so covering a grid in the plane, but that wasn't actually the full version of the original theorem of Allen and Freddy. They considered a generalization where you work in higher dimensions, and instead of covering with lines, you cover with hyperplanes, so codimensional 1 subspaces. So in the plane, a hyperplane is a line. It's dimension 1 inside a dimension 2 space. But in general, if you have a d-dimensional space, then you cover with d-1 dimensional subspaces, or hyperplanes. Okay, so they proved, it's not super important what this says, but it's just the same type of statement, that you have some finite grid in d dimensions over an arbitrary field, and you have a forbidden point inside the grid, and now you want to cover all of the points on the grid with hyperplanes except this forbidden point, then the number of hyperplanes you need is essentially the sum of all the dimensions minus 1. Okay, and in 2 dimensions, this is precisely the statement we saw previously. Okay, so nothing changes. And again, if you didn't have a forbidden point, then it would be trivial. You just take the smallest dimension, and you take parallel hyperplanes covering the slices. Okay? So this was the Allen-Furedi theorem, and again, this is the best possible bounds. So the proof was algebraic to show that you need at least this many hyperplanes, and then it's easy to construct a hyperplane cover with this many. You just take the kind of parallel hyperplanes in all directions that avoid the forbidden point. Okay, so you get 1 less than the size of each dimension. So they weren't interested in Pacman, right? That wasn't why they proved this theorem. So they had some combinatorial motivation. So there's a paper of Komiath who is studying infinite Ramsey theory. And if you don't know what Ramsey theory is, then take a combinatorics course and you'll find out. It's a very, very fascinating area of combinatorics with many surprising results and applications as well. Okay, and so Komiath was a Hungarian mathematician. He was looking at some infinite Ramsey theory, and he needed this problem in the case where you're looking at the hypercube, so 0, 1 to the d, in the real space, in the Euclidean space. And all he needed to show was that the number of hyperplanes you need goes to infinity as the dimension increases. Okay, so again, if you're just trying to cover the entire hypercube, then you just need 2 hyperplanes, right? They're like x equals 0 and x equals 1. But now that you have this forbidden point, the point of the theorem is that you need very many hyperplanes all of a sudden. And so Komiath needed to show that you needed an infinite number of hyperplanes as your dimension grows. Okay, and he was able to prove some bound, I think maybe logarithmic or something like that. And then Allen and Furedi, in their paper, which came out roughly the same time as Komiath's paper, they showed that actually the minimum number of planes you need is d. Okay, so they proved a tight bound for this problem. But this type of problem has been studied in a specific case by finite geometers a few decades earlier. So if you're working in a finite field, okay, and your grid is the entire finite field, because now if you're over a finite field, your space is finite, so you only have finitely many points. So it makes sense to ask this question for covering everything except 1 point. And this turns out to be equivalent to what are called blocking sets, where you're looking for, instead of covering points with planes, you're looking for points that cover all the planes. Okay? And so there's a 1-to-1 correspondence if you use some duality. And so this was a question which was studied or first answered in the 70s by Jameson. And again, he used a polynomial method, okay, to answer this. So this was another special case of the general Allen-Furedi theorem. Okay? And as I said before, the significance of this theorem, so it's a nice result, and of course to get an exact answer, but the reason why it became so important and so popular and well studied is because it developed the polynomial method. Okay, so this wasn't something which had been used much before, and so this introduced this idea that you can use these polynomial results or this algebraic method to solve combinatorial theorems or problems which have nothing to do with algebra. Okay, and so it made it popular, and so whenever somebody would kind of develop a new version of the algebraic method, it was very often that they would test it on this grid covering problem to see what it gives you. Okay. So it was an important problem. It came up in the 90s, in the combinatorial setting at least, and there has been a lot of attention paid to it ever since. Okay? So that's the kind of classic background. Okay, so that's the kind of stuff which you'd maybe meet in a combinatorial course. And so now we're going to move on to the second part of the talk, which is about the more recent developments in this problem. Okay? And this is a multiplicity extension. So in the original problem, we wanted to cover every point at least once except for one forbidden point, which we weren't allowed to touch. But now you may not be satisfied with covering it just once. Well, the question is, what if I need to cover all the points many times? Okay? And we saw earlier when we had this construction with the horizontal and vertical lines that most of the points were already covered twice. Okay? But there were some points which were only covered once, those on the x-axis and the y-axis. And so then the question is, well, if I need to cover every point twice, but avoiding the forbidden point again, how many lines do I need to do that? Okay. And so we'll introduce a bit of notation just to be able to write some formulae. So again, if I have some finite grid, okay, over some field, I'll always write the grid as gamma. Okay, so it'll be a Cartesian product of the finite sets, and I'm going to assume the forbidden point is the origin, so each of these sets contains the coordinate 0. Right, and again, given any grid, I can always translate it so that the forbidden point sits on the origin. So that's not a restriction in any way. Okay. So then I'm going to call a K cover of gamma a set of hyperplanes which cover all the points of gamma at least K times except for the origin, which isn't covered at all. Okay? So the hyperplanes have to avoid the origin, and they cover all the non-zero points at least K times each. Okay? And notice that I'm calling it a multiset because I'm going to allow you to use the same hyperplane multiple times if you want. Okay? And then the K cover number, which I'll denote cov K of gamma, is the minimum number of hyperplanes you need to, in a K cover. Okay, so it's the same question as before. What is the minimum number of hyperplanes? But now I want to cover every point K times instead of just once. Okay, and I still avoid the origin completely. Okay, so now the question is, given gamma, how small can K, or what is the value of cov K? Okay. So there are some simple bounds we can write down without any thought, okay, or with bare minimum thought. And the first, let's look at the upper bound. So if I want to cover all the points at least K times, then if I have a set of hyperplanes that cover all the points at least once, I can just repeat all of those hyperplanes K times. Right? And then because every point was covered once originally, it will now be covered K times when I repeat it, at least K times. Okay? And then the number of hyperplanes grows by a factor of K. So if I know the answer for covering things one time, then an upper bound for covering things K times is to just take K times the original cover. Okay? So that gives me an upper bound. Now it might not be very efficient, okay? So we'll ask, is this a good upper bound? Okay, but it at least shows that this number is finite. And so what about the lower bound? Well, if I take a K cover, so if I have a set of hyperplanes that covers every point at least K times, then I can remove any K minus 1 planes from that cover, and every point will still be covered at least once. Right? Because originally it was covered K times, I only lost K minus 1 planes, so there still must be at least one plane which covers that point. And so if I take a K cover and remove any K minus 1 planes, I still have a 1 cover. Every point is covered at least once, so I still have at least the 1 cover number of the grid. So that shows me that the original cover, at least the 1 cover number, plus K minus 1. Okay? So this shows the upper and lower bounds of this K cover number, that they're kind of related to the 1 cover number, but here I'm only adding K essentially, and here I'm multiplying by K. Right? So that gives me quite a big gap between these bounds. Okay? I should say also, of course, at any point if you have any questions or something's unclear, please do feel free to ask. Right? Don't hesitate. So now, those were some very simple bounds. You could say those are combinatorial bounds. We're not using any complicated mathematics, but you could say that, okay, the 1 cover number, we were able to solve it using these polynomials. So can we use the polynomials for K covers as well? And it turns out that you can, okay? Because if you think about how we constructed the polynomial, we said that, okay, for every line I get a linear factor, and then I take a product of the linear factors, okay? Or in general, for hyperplanes, I get linear factors. And so now, if I'm covering every point at least K times, then at that point, I get not just a 0, but I get a 0 of multiplicity K, right? Because at least K of these linear factors will be equal to 0. So I get a 0 of higher order at this point, and now that gives me some more algebraic information, and so I can use that to get a better bound. Okay? And so you can analyze the polynomials, you get some better bounds in the degrees, and then this was done in general by Ball and Serra, okay? And they proved that for any grid gamma, the K cover number, so this is the Alon-Furedi bound, right? This is the 1 cover number that you get at least the sum of the dimensions minus 1. Now our trivial lower bound was to say you add K plus 1, right? Because I can throw away K minus 1 planes and still have a 1 cover. But now Ball and Serra showed that if you use the algebraic method, you don't just add k minus 1, but you add k minus 1 times the largest dimension. Okay? So it gives you an improvement on this trivial lower bound. Okay? But it's not clear how tight this bound is. Okay, so with the Allen-Furedi bound, we could show that it was tight, right? That it was very easy to construct covers that match that for any grid. With the Ball-Serra bound, it's not so clear. Okay, whether it's tight or whether you can improve it. And so if we look at a special case of the hypercube, right, we mentioned this as the original motivation for Allen and Furedi. So now your sets are 0, 1, and you're looking at the d-dimensional hypercube in the real plane. But now instead of the 1 cover, we want a k cover gamma. Okay? So then Allen and Furedi showed that for 1 covers, you need at least d hyperplanes in d dimensions. And that means, again, by our trivial bound, a lower bound on the k cover number is d plus k minus 1. And notice that Ball and Serra doesn't give you any improvement here. The previous theorem we said, because you get k plus 1 times the maximum dimension minus 1, but each dimension here is just 2. Right? So you multiply k minus 1 by 1, and that doesn't change anything. So we get this trivial lower bound again, and then we get the trivial upper bound of k times d, where you repeat every k cover k times. But then kind of this problem came back to life, or it attracted a lot of recent attention in a paper of Clifton and Huang. So they studied this setting, and what they could prove is that using these algebraic methods, they improved the lower bound from the trivial d plus k minus 1 to d plus k plus 1. Okay, and the way they did this is, again, they looked at the polynomial, they used a Null-Stellensatz type theorem, okay, and they used it specifically for the setting in order to improve the bound. Okay? So you're only gaining plus 2 in the lower bound, but it was a significant amount of work. And for, like I think for k equals 4, for example, this is tight, if I'm not mistaken. Or there are some ranges where this gives you the right answer. Maybe not k equals 4, sorry. And then in the upper bound, they improved it to d plus k choose 2. And this was an explicit construction. Okay, so here you get k times d, but here it's just d plus k choose 2. So if you think about d, the dimension as going to infinity, and k as being fixed, then this shows that the answer is d plus a constant depending on k. But the constant in the lower bound is linear in k, and the constant in the upper bound is quadratic in k. Okay, so there's still a gap between the bounds, and they conjecture that this is the correct answer. Okay, that the d plus k choose 2 is the right answer, but at least from the algebra, it's not clear how you could get there. Okay. But so I compared the bounds. They also looked at the other way of changing these parameters, where you fix the dimension, but you increase how often you need to cover the points. So now d is fixed, and the multiplicity k goes to infinity, and here they were able to determine the k cover number asymptotically. Okay, so as k goes to infinity, they show that this is how the k cover number grows for a fixed hypercube, and then this is the harmonic series here. So as d is growing, this looks like k times log d. Okay, so this behaves quite differently from this setting, where the multiplicity is fixed and the dimension grows. Here you invert that order, so you fix the dimension, you let the multiplicity grow, and there they could essentially answer the problem. So this is asymptotic, but then for certain nice values of the multiplicity k, you get the exact answer as well. So without the lit low of 1. Okay? And then the interesting thing here is that they didn't use algebraic methods for this case. Okay, so this they proved using some linear programming techniques. Okay, so from optimization theory, which I'll cover later on. Okay. So as I said before, for the original Allen and Furedi theorem, the only known proofs are algebraic, but here they were able to answer this multiplicity version without using algebraic arguments. Okay, so it seems to be quite a different type of problem. And then there was some subsequent work. Okay, so as I said, Clifton and Huang, they kind of reinvigorated this field of research. And so Saarman and Vigdorson, in a very impressive piece of work, they answered the polynomial version of this problem. Okay, so the problem we're looking at is geometric. You have a grid and you want to cover the points. But as we said, you can reduce that problem into an algebraic problem by taking a polynomial. And now there's a purely algebraic question where it says, suppose I have a polynomial which is non-zero at the origin, and vanishes to order at least k at every other point on the grid, how small can the degree of this polynomial be? Right? So now this is just an algebraic question, and this is the question that they answered. And they showed that the answer is d plus 2k minus 3 in a certain range of parameters. So notice that this is different from what Clifton and Huang conjectured that the covering problem should be. Because Clifton and Huang say it should be d plus k choose 2. So this suggests that in fact the two problems are different. So in the Allen-Furedi setting, when k is equal to 1, you get the same answer for the polynomials and the covering problem. But if you want higher multiplicity, then it's somehow different. And because there are polynomials which aren't just a product of linear factors, right? Whose irreducible polynomials have higher degree, and these are maybe more efficient for covering the points. Okay? But you cannot realize them as hyperplanes. And then in kind of our work that I did after I moved here to Taiwan, we proved some stability for the Clifton-Huang result. Okay, so Clifton and Huang, so this is in the second range, where they get the exact answer, the asymptotic answer. So you fix the dimension and your multiplicity grows. They said that, okay, you need k times log d many hyperplanes, and there are covers of this size. So what we were able to show is that if you have a cover of this size, or close to this size, it has to use some special types of hyperplanes. So you could describe precisely what kind of hyperplanes you're allowed to use, and then using these precise results, we are able to determine the cover number for almost all multiplicities when you look at the 6-dimensional hypercube as well. Okay, so Clifton and Huang did this for d equals 5, and so we extend the result to d equals 6. Okay. And then there is another piece of work we did when I was in Germany as a postdoc, and there, instead of looking at this problem over the real numbers, we considered this problem over the finite field F2. Okay, and that's more like the finite geometry setting we talked about earlier, because now the hypercube is the whole space. Right? So F2 is 0, 1. And what we were able to, or kind of what we showed, is that this problem is now equivalent to a problem from coding theory. Okay, so it's a problem about finding linear codes with large minimum distance. So if you're familiar with coding theory, you'll know this problem because this is the fundamental problem in coding theory. Okay, it's very important for many applications, and it's a long-standing open problem. Okay, so it's a very difficult problem, right? So we didn't solve it, right? Otherwise, I wouldn't be talking about grids, I'd be talking about codes. But we were able to use this connection to improve what's known in the grid covering problem. Okay, so we looked at a variant where instead of not covering the origin at all, you just wanted to cover it less than k times. Okay, and we could solve that problem. So these were kind of some results that have been done since the Clifton-Huang paper, but what I want to talk to you today is about a specific setting which hadn't been studied much before. Okay, and so this is coming back to our original setting where we're looking at a grid in the real plane, okay, but now we want to k-cover the points. Okay, so we want to cover the points with multiplicity, and we were very surprised to see that this hasn't really been studied systematically, at least. Okay, we would have it's a very natural problem in our opinion. We would have expected there to have already been an answer, but there didn't seem to be one. Okay? And so again, if you look at kind of the bounds we had before, you can get our bounds, okay, or you can get some bounds. So kind of this is the Balsera bound, okay, because notice that n minus 1 plus m minus 1 is the Allen-Furedi bound for one covers, but now because with the Balsera you get essentially this k minus 1 times the largest dimension. Okay, so you get some significant improvement, but then the trivial upper bound where you just repeat the one cover k times, you also get a k times the m minus 1 here as well. So there's still a gap between the two bounds. Okay, so this is Balsera, this is the trivial upper bound, and so then the question was, well, when is this Balsera lower bound tight? As we said before, it's not clear if it is tight. So are there grids where it's tight? And if it's not the right answer, then what is the right answer? Okay, how much can we improve the lower bound? So we got quite a few results here in this setting. So the first thing we were able to show is that if your grid is very stretched out, so if it's a lot wider than it is tall, so if your n is much bigger than m, then the lower bound is tight. Okay, so this is our first result. So if you have n being significantly larger than m, okay, by a factor of k minus 1, then for any m by n grid, the cover number is what Balsera says it should be, or what it is at least. So the lower bound here is already known, that's Balsera. We just need to prove the upper bound, which is an explicit construction. Okay, and it's not hard to see what the construction is. So you take your grid, and you take every horizontal line once, except the one line you're not allowed to take, and you take every vertical line k minus 1 times. So now, with these lines, almost all the points in the grid are already covered k times, once horizontally and k minus 1 times vertically. So what is left? Well, these points here are only covered k minus 1 time, so they need one more line each, whereas these points here are only covered once, so they need k minus 1 lines each. But the point is that I have many more of these lines than I have these lines by my condition on n and k, n and m rather. So I can just take these lines to cover pairs of these points. Okay, so for every point here, I take a line to one of these points here, such that each of these points is used at least k minus 1 times, and each of these points is used once. Okay, and then I get a valid cover, where everything is covered k times, and when you count up the number of points and lines you use, you get precisely this. Okay? So it's a fairly simple construction, but it shows that if your grid is very stretched, so it's very rectangular and not square, then the known lower bound is in fact tight. But now you can ask, well, do you really need this condition? Right? We needed it for our construction to make sure that we could match up these points and the axes without any waste, but maybe there's a better construction which doesn't need this n to be so big. So then in our next result, we showed that in fact you do need this condition. Okay, so we showed a different lower bound, okay, from the Balsera lower bound, and it looks a bit complicated. You don't need to worry about what it says, okay. But what we could show is that for many choices of parameters, this is in fact a tight bound. Okay, so this is the best you can do, and you can, if you do the calculations, if you compare this to the Balsera term, which is just m minus 1, you see that this will be bigger than m minus 1 if and only if n is smaller than the threshold we had before. Okay, so again, if n is at least k minus 1 times m minus 1 plus 1, we know that the Balsera bound is tight. But if n is smaller than that, then this term here is bigger than m minus 1, which is what Balsera gives, so we prove a lower bound, which is better than the Balsera lower bound. Okay, so that shows that Balsera is not tight. Now there's one caveat, okay, that here I say this is true for almost all grids. So there could still be grids where Balsera is tight, but we know that it's not tight for every grid. Okay? But now the question is, what do you mean by almost all, right? Because there are infinitely many grids. Okay, so I need to be precise about this. So we define what we call generic grids. Okay, so we say a grid is generic basically if when you look at points, when you look at lines which go through both axes, they don't contain many points inside. Okay, so here I've taken a random grid. Okay, I chose these coordinates at random, and now if I look at any line, it'll only contain the axis points and it won't contain any internal points. Okay, and this is true for any such line. And so you can show this quite easily if you take random coordinates according to some continuous distribution, then with high probability the grid will be zero generic. Right, and that makes sense intuitively, because if I have a line which does contain a point, that means I have some algebraic relation between the coordinates, but that's not going to happen if I choose random coordinates. Okay, and that's what we mean when we say almost all grids, that if you look at a random grid, it's going to be generic, and then for these generic grids we can prove our lower bound. Okay. And so one thing we saw in our lower bound, let me maybe go back. So here we get this additional term, and this additional term is in terms of m, which is the smaller of the two dimensions. So kind of the worst case is what happens when m and n are equal. So you have a square grid with the same number of points in both dimensions, and so then this is what we focused on next. So if I have a square grid, what kind of bounds can I prove? And so we proved, and so these are kind of the original bounds. So this is the trivial bound, this is Balsera. Now everything is just in terms of n. So we proved the general upper bound, so this works for any grid, that instead of 2k, which is what you get from the trivial bound, it's enough to take 3/2 times k. Okay, so we shave a constant factor off. And then for a lower bound, we could prove that any grid has this as a lower bound. Okay, and this is a somewhat peculiar looking number, but the point is that it's strictly bigger than 1. this coefficient. Right, so the previous lower bound of Balsera is, essentially 1 times k times n. And now here we improve again by a constant factor. Okay, so again we show that for square grids, this lower bound is not going to be the right answer. And then we can do more. So if the grid is generic, right, so if it's this kind of typical grid that we defined earlier, then we can improve the lower bound to this factor here. Okay, and in particular, if delta is equal to 0, for example, this becomes 2 minus 1 half. So we get 3 halves, which is the same as we have here. So we show that for generic grids, 3 halves times k times n minus 1 is the right answer. Okay? And in fact, you don't need delta to be 0. It's enough if delta is sublinear. Okay? And that's useful. So there are some perhaps reasonably natural grids that you could look at, which are lit low of n generic. So it's easy to see that the exponential grid is 1 generic. And then, as I was mentioning again at t, using some number theory, you can show that if you have this quadratic grid, then that will also be lit low of n generic. Okay? So for these grids, and for almost all grids, the answer to the covering problem is 3 halves times k times n minus 1, so about halfway between the existing bounds previously. Okay? So those were kind of our main results about square grids, but kind of there's one obvious grid, which is the natural grid you want to look at. And that is what we call the standard grid, where things are evenly spaced. Okay, so it's a subset of the integer lattice, an initial segment. And the problem is that this is not a generic grid. Because if I look at these diagonals, I contain many points from inside. Okay? So if we used our previous bounds with delta equals n minus 2, we get nothing useful. So then we studied this grid in particular, and we tailored our methods to this grid, and we were able to prove some improved lower and upper bounds for this problem. Okay, and again, we see some rather odd-looking numbers, but if you calculate them numerically, we see that the numbers aren't so far apart. Right? So the lower bound is 1.39, upper bound 1.41 essentially. Okay, so there is still a gap between the lower and upper bound, but in particular, this is smaller than 3 halves. So it's easier to cover the standard grid than it is to cover general grids. And again, you'd expect that because there are lines which contain many points. So you can cover them more efficiently. And on the other hand, again, this lower bound is improved from the original bounds we had, right, of essentially 1. And moreover, we can show that this is the right answer if you only look at covers which use lines of slope 0, so horizontal lines, infinite slope, so vertical lines, and slope minus 1, so these kind of diagonal lines. Okay? And that's significant because to prove the upper bound, we construct a cover which only uses these kind of lines. And now we can show that if you only allow yourself to use those kind of lines, then this is the best you can do. Okay. So are there any questions about the results we prove? Okay. So hopefully the nature of these results is clear. And so I'll just say a little bit about the proof methods that we used. Okay. So again, we want to bound the minimum number of lines you need in a K cover. Okay. And so for upper bounds, we construct K covers. Right. So we say, okay, if this is your grid, here's a set of lines which covers all the points, at least k times, except the origin. And these are explicit constructions. Okay, so we can define the lines explicitly, and we show that they have at most the number of lines we claim. Now for lower bounds, you need to show that there cannot be any k cover with a small number of lines. Okay, and in the Allen-Furedi thing, you did this algebraically, but here we use this linear programming technique, which Clifton and Huang used. Okay, and it comes from counting point line incidences, but doing it with some weighting. Okay, so because I'm running a little lower on time, I'll only talk about the lower bound now. So as I said, the upper bound was from explicit constructions. Okay, so they're not particularly difficult. Okay, and the more interesting part is improving the lower bounds. Okay, so how does this weighting work? Well, we have these points on the grid which we want to cover, but not all the points are created equal. Some points are easier to cover than other points. So when we want to count how big a cover needs to be, it makes sense to count the difficult points or to give more importance to the difficult points. So we're going to introduce some weighting, which is a weighting of the points on the grid, assigning them all a real value, which is about how important we think these points are. Okay? And then we will define the weight of any set of points to be just the sum of the individual weights. And now what we claim is that if you have a weighting such that every line has weight at most 1. So if you look at the points on the line, then the total sum of the weights is at most 1. Then the number of lines you need to k-cover the grid is at least the k times the weight of the whole grid. Okay? And then this is a simple counting argument, because if I fix a k-cover, the smallest possible k-cover, I'm going to count the point line incidences. So I'm going to count pairs of a line in my cover and a point on my grid that lies on the line. Okay? And I know that each point is covered at least k times. So when I look at these point line incidences, that point is there at least k times. And then every time it's there, it provides the weight w of x. And so if I sum up all the incidences, I get k times the sum of the weight of the whole grid. Because every point in the grid is there k times or more. Okay? I should say that the weighting is non-negative, actually. Right? So you can't get cancellation. So this gives me a lower bound of the weight of the point line incidences. But on the other hand, every line in my cover gives me weight at most 1. So if the total weight is at least k times the weight of gamma, then the number of lines needs to be at least k times the weight of gamma. Right? So I can translate counting lines into the weights of these points. Okay? And so if I want to get a good lower bound, I want the weight of the grid to be as big as possible. Okay? But I have this condition that no line should have weight more than 1. So this turns into an optimization problem. Okay? And if you're familiar with linear programming, this is a dual program to the covering problem. Okay? Or the relaxation, fractional version of the covering problem. So this is our objective function, or this is our optimization problem. We want to define some weights on the grid, maximizing the total weight, but with the condition that every line has weight at most 1, so that my previous proof works. Okay? And now to get a lower bound, I just need to give you a weighting. Right? So if I say these are the weights of the points, I can count what the total weight is, and I get a lower bound for my covering problem. So that's what we do for our various bounds. Okay? So for example, here's a kind of easy warm-up. I can prove that the k-cover number is at least 1 plus 1 over n times k times n minus 1. How do I do this? I give every point weight 1 over n. And in an n by n grid, any line can contain at most n points. And so the total weight of the line is at most 1. So this is a valid weighting. And then I count the total weight. I have n squared minus 1 non-zero points. Right? So that's n plus 1 times n minus 1. And then I divide by the n because the weight of each point is n. Okay, so this gives me this bound immediately for any n by n square grid. And it's not a very impressive bound, right, because this constant is 1. As n grows, this tends to 1. But this does already beat the Balsera bound if k is bigger than n. Okay, so it's perhaps a non-trivial bound. Okay, but we could do better, of course. All right, so we can prove that if you have a generic n by n grid, then you get this 3 halves, which I claimed. Okay, so this is a simplified version of the delta generic bound, which I showed earlier. And again, it's a very simple weighting. For the axis points, I give weight 1/2 to all of them. And for the interior points, I give weight 1/2 time, divided by n minus 1. Okay? So now, why does this work? Well, if I have any line, if it contains 2 axis points, then it has 2 points of weight 1/2. But because this is a 0 generic grid, it won't contain any other points. So then the weight of that line is 1. And on the other hand, if it contains at most 1 axis point, then it has at most n minus 1 of these points. And so again, the total weight is at most 1. Okay, and if it contains no axis points, then it has at most n of these points, so then it's even less than 1. Okay, so again, it's a valid weighting, and then you sum up the total weight of the points. From the axes, you get essentially 1, and then from these points, you get another 1/2. So that's where the 3/2 comes from. Okay. So again, this gives you a very simple proof of the lower bound once you find the right weighting. Right, so the challenge is to find a good weighting for this problem. And so, yeah, how do you find these feasible weights? Okay, now for the standard grid, right? Because the standard grid, remember, that was the problem where we couldn't solve it exactly. We got some bounds which are a bit different. So, you know, if you're stuck, you try to be clever. And if you can't be clever, you try to let someone else be clever, namely your computer. Right? So we ran some integer optimization problems, some linear programming optimization to find the right grids. And so, for example, this was for the 12 by 12 grid. This is the answer we got. Okay? And we looked at this a bit, and I invite you to look at it as well. If you can see any sort of pattern which explains what these weights are, then please let me know, because we couldn't. Right? These look completely random to us. You can see a lot of the weights are 0, but then a lot of these weights are non-zero, but they're just some nasty numbers. They don't look very familiar to us. Okay? And one of the problems is that this is a very high-dimensional problem. You have many degrees of freedom, right? Because every point gets a weight, but your number of restrictions is not so big. Right? So there are going to be possibly many optimal solutions or near optimal solutions. So the computer, of course, it doesn't have any sense of what is a nice weighting. Right? All weightings look the same to the computer, and so it's just going to give you an arbitrary solution. Okay? And then it's very hard to get something meaningful out of that. So yeah, we weren't able to find an optimal weighting for our problem because they don't look very nice as far as we can tell. But what we could do is we could find some more human weightings where we could prove a lower bound. Exactly. Okay, so for example, I claimed this lower bound on the standard grid. Okay, and I can write down what the weighting is. Okay, so on the axis points, I'm going to give 1/2, just like before. Now, remember on the standard grid, this is problematic because I do have lines which contain 2 axis points and many internal points. Okay, so those internal points then have to get weight 0 because I already have 1/2 from each of the axes. So if I have a point which is in the lower triangular half of the standard grid, I have to give it weight 0. But now when I have points above the main diagonal, those aren't in any line which contain 2 axis points. So I can give them some weight, and I will give them weight 1 over n minus I, which is the length of the main diagonal there. Okay, and I do this for some of the diagonals, not all of them. And then you choose some, you kind of choose it to optimize things so that this gives you a valid weighting. Okay, and then if you do the calculation, you end up with this 2 minus 1 over the square root of e. Okay, so a little bit of an odd number perhaps, but as you can see, you get some sort of harmonic sum here, and that's why this exponential appears. Okay, so this is how you can prove these more complicated lower bounds. And then, as I said, if we had the restricted problem where we only use horizontal, vertical, and slope -1 lines, then we could prove a matching lower bound to our upper bound. Okay, and that was again by constructing a weighting, but that was a much more complicated weighting, okay, where we had to define things recursively, and so I'm going to spare you the details of that. Okay, so just to summarize the results again, the Baltzera bound was the previous known bound, and I should say the Baltzera bound, again, it works in general. It's not just for the 2-dimensional grid that we studied, but in the 2-dimensional case, we could say when it's tight, and we could show that it's not tight when, for smaller or for squarer grids. Okay, and then for square grids, we could give some general lower bounds that improve Baltzera, and we could determine the answer for almost all grids. Okay, which was this 3/2 times k times n minus 1. And then for the standard grids, we gave some non-trivial upper and lower bounds, which were fairly close to each other, and we showed that the upper bound is tight when we restrict to the types of k covers we could find, okay, by computer searches. And so there are quite a few open problems left, if any of you would like to work on this problem. So of course, the kind of outstanding problem is the standard grid. What is the correct answer? We believe that the upper bound should be the correct answer. Okay, so we weren't able to find a good weighting which gave us the square root 2 in general, but we do think that that should be the best possible. Okay, and the weighting which we used to prove this in the restricted case, we know that that doesn't work in general. Right? So it's not that we weren't able to do the calculations, it's that that weighting just doesn't work. And then, without determining what this answer is exactly, we think that maybe this is the worst case, in the sense that this is the grid which is the easiest to cover. So one kind of extremal question you could ask is which grid gamma minimizes the k cover number? And we would think maybe it is the standard grid gamma n, because again, this allows you to have lines which cover many points at once. Okay, so it's a fairly natural guess, but we don't know for certain, right? So this, I would say, is a conjecture. This one is just a question, where we're less confident in the answer. And you could also look at this in higher dimensions. So as I said, Baltzera exists in higher dimensions. So we looked at the 2-dimensional case here because there are still many open problems. What happens in higher dimensions? When is Baltzera tight? When it's not tight, what can you prove? So one of the authors, Yvonne Den Bakker, she was a master's student when we were doing this. So in her master's thesis, she also looked at some results in 3-dimensional settings. Okay, but generally, in 3 or more dimensions, most of the stuff is open. Okay, so you can answer these types of questions. And then finally, what happens if you don't work in the real, right? So if you look at finite fields, for example, how much do the answers change? And as we saw with the hypercube setting, the answers look very different in the real case versus the finite field case. Okay, so is that still true here, and what can we prove? Okay, so these linear programming methods, they don't really work so easily in the finite field setting. Okay, so that's all. Thank you very much for your attention, and I'd be happy to take any questions.
So, any questions or comments?
I wonder that if our multiplicity is larger than 2, could we always throw the color down exactly with J line, where J is larger than our lower bound and is less than our upper bound?
What do you mean by draw the cover down?
In two-dimensional case, we draw linear lines, and could we exactly draw the cover which use J lines, where J is in our desirable interval?
Yes. So you can, if you have a cover, right, the smallest possible cover, you can always add lines to it to get a larger cover, right? Because if you add lines, it'll still be a cover. You still cover every point.
Yeah.
So for a kind of cheap answer to your question, if I know the minimum number, which is the k cover number of the grid, then for any number bigger than that, I also have a cover of that size. Because I just take the smallest cover and I add some arbitrary lines, right? So that's not a very good answer, right? Because it's not very interesting. But there is a very interesting question there if I look at minimal covers, right? So here I was interested in the absolute smallest cover in terms of number of lines, but you can also talk about minimal covers where it's a cover, but if I remove any line from the cover, it's not a cover anymore, right? And now there, it's a very interesting question, what are the possible sizes of a minimal cover, okay? Because then I cannot do this trick, right? I cannot just add arbitrary lines, because then I could remove those lines and I still have a cover. So if I have a minimal cover, how many lines do I need to have? And I don't know what the answer to that would be, right? So there are certain questions that people ask in this type of direction. So for example, in the hypercube setting, the Allen-Ferretti bound gives you an answer where you take kind of these parallel planes, right? So x equals 1, y equals 1, z equals 1, and so on. Then there are questions that people ask, okay, what if I have somewhat, symmetric covers or things like that? How does the answer change? And then depending on the restrictions you put, you can get much bigger bounds instead. So it's certainly an interesting question, what minimal covers look like. And there you might ask, instead of looking for the smallest cover, what is the biggest minimal cover? So it's a cover where everything is covered 2 times. There's no redundancy. So if I remove any line from my cover, it's no longer a 2 cover. So one point gets covered only once. But now, what's the maximum number of lines that this could take? Okay, and that would be a very interesting question. These types of questions get asked in other extremal settings, in graph theory and things like that. And I wouldn't know what the answer would be to that. I don't know if anybody has studied it. So it would certainly be an interesting question.
So, any other questions? So, I have one. So, in your setup, you only allow 1 forbidden point. So, what's no for the case where more than 1 forbidden points are allowed?
Yeah, that's also a very good question. So in fact, the Allen-Ferretti theorem is even more general than what I showed, or their results at least. So what they showed is that, okay, if I want to cover the grid, except for 1 forbidden point, then I need at least this many hyperplanes. And they also said that if I have fewer hyperplanes, they gave a bound on how many points are left uncovered. Okay, and that bound again can be tightened. So they said that, okay, so for example, in the n by m grid, they said you need at least n plus m minus 2 lines. And then they said that, okay, if I have n plus m minus 3 lines only, then there have to be at least this many points uncovered. Okay, and they prove a bound there. And so those bounds can be tight, okay? But again, it'll be a very specific set of points which you leave uncovered. So there have been problems, usually in the hypercube setting, so 0, 1 to the d, where people say, okay, if I don't cover, if there are 2 forbidden points, how many lines do I need? Okay, or if there are 3 forbidden points, how many lines do I need? So I think for 2 and 3 points it's characterized. We know what the answer is. For 4 or more points, there are some bounds, I think, which are sometimes tight, but sometimes then it starts depending on which points are forbidden. One of my co-authors, Professor Lin, Dr. Lin, he and his master's student, they looked at some of these problems, and they gave some points there. Yeah, so there are some results known, and it does depend on, when you have, I think, if you have 3 or more points, it'll start depending on what those points look like. Right? Like, for example, in the grid, do they lie in a common line? Then you get one answer, and if they don't lie in a common line, then you get a different answer instead.
Okay, so any other questions? So if there's no further question, let's thank Shagnik for his wonderful talk.